Good morning. Thank you all very much for coming today. We have a really interesting talk scheduled for you today. I'd like to introduce Professor Jim Buckwalter from UC San Diego. He directs the high-speed IC lab at UC San Diego. His main research interests are RF and millimeter wave design for two different applications that he'll talk about today, wireless applications and also optical electrical interfaces, which should be pretty interesting. He's recently won a couple of very high-profile awards. One is the 2007 DARPA Young Faculty Award, and recently this year he found out that he won the NSF Career Award as well. So let's go ahead and welcome our speaker, Professor Buckwalter. Cool.
Thank you, Brian. Welcome. I'm happy to see so many people here, but I guess it's the beginning of the term, so you're not too worn out yet. I'm basically covering a lot of material in today's lecture to give you a good feeling for what we're doing down at San Diego on the topics of high frequency and high speed, which we basically divide into two categories. And my students, who I like to give credit for this work at the beginning of the talk rather than at the end, are broken into that kind of framework. Some of them are working on very high frequencies, so maybe narrowband systems at hundreds of gigahertz. And some of them work on building very broadband, very high-speed systems that can transmit data at 40 to 100 gigabits per second, the kind of data capacities that will be needed in future communication networks. In this talk, basically, I'll be breaking it into two different portions to correspond with these two different divisions of research. One on bidirectional millimeter wave circuits, and one on high-speed integrated optical circuits. And in this area, we're basically doing some very novel work on manipulating light on silicon substrates, so with silicon integrated circuit processes. For the first portion of the talk, I'd like to describe millimeter wave applications and circuits that support those applications. We're basically looking at some modern applications that you probably are aware of. Things like high-capacity communication, 77 gigahertz car radar for doing automotive cruise control. These things you've started to hear about probably as products. You can buy 60 gigahertz links for TVs now. 77 gigahertz radars are starting to turn out in high-end automobiles. But there's another set of millimeter wave applications that are kind of on the horizon. Things like point-to-point backhaul at E-band, E-band being 70, 80, 90 gigahertz bands, where you can basically beam 10 gigabit per second links between two buildings, skyscrapers essentially, or across a vast area of desert, and provide very high-speed communication to areas that weren't previously getting internet. And so there's a lot of opportunity in this backhaul to not only improve the current infrastructure of cellular communication, but to also provide communication to people who didn't previously have it. Another area that's very interesting in the future is 94 gigahertz and above, into the terahertz regime, where imaging promises to open new applications for not only security imaging, things like going through the TSA scanner at the airport, which is already coming out and is shown here in this picture, where they get very, very clear images through clothing and through backpacks, but also for medical imaging at even higher frequencies, where you get a very shallow penetration depth that allows you to detect things like cancer and cavities. When we talk about silicon processes, we're basically talking about two categories of devices that fall into the umbrella of a silicon process. We'll be discussing in this talk a silicon germanium transistor, a heterojunction bipolar transistor, which is a little more exotic than mainstream CMOS silicon. But this process provides a transistor that has a speed of about 210 gigahertz. But its main advantage is that it has a breakdown voltage that's a little more than 2 volts. But there's another process that's making a lot of headway in the frequency regime that we call millimeter wave, and that's the 45 nanometer SOI NFET, which has an FT that's about 370 gigahertz. And I put an asterisk there because that's at the very, very tippy top of the frequency speeds that it can achieve. But the bad thing about this 45 nanometer NFET is that its breakdown voltage is about 1/2 of what you can achieve with the SOI NFET. So they're very comparable. They trade off with one another very nicely. And we'll talk about how they address the future of millimeter wave integrated circuits. When we look at how we're going to compete what the existing technologies are in this area, they tend to be 3-5 material systems, things like gallium nitride, which you may have heard of for high power amplifiers or even for white LED lighting. Gallium nitride is a very, very exciting material. And typically what we see for output power going from 20 to 100 gigahertz is that gallium nitride amplifiers are basically about 12 dB better in terms of output power. And that's a big difference. 12 dB is the difference between 1 watt and 10 watts. And essentially, in the long run, is the difference between being able to transmit over a few hundred meters and a kilometer. But when you look at efficiency, this picture is a little different. Silicon and gallium nitride processes are very competitive in terms of efficiency. There's no great difference between using a 3.5 or using a silicon material process. So what we really need to overcome is this power gap. And there's a few ideas that have been floated out there, some are old and some are new, about how we can get silicon to beat these 3.5 material systems. The first is heterogeneous packaging. This might be a silicon chip and a gallium nitride chip sitting next to each other, and they're wire bonded together. That's been around for some time. It's very expensive, but it can be done, and it's pretty successful. The second, which is starting to gather some attention, is heterogeneous processing, where we'll have a silicon process and we'll grow a 3.5 transistor on top of that silicon process. So we still have a single chip. And this has required some manipulation of the standard silicon process, but just now is starting to introduce some exciting new avenues. The third is on-chip power combining, where we might have a bunch of small silicon PAs that we combine. And to get 12 dB more power, you basically need to combine something about 10 to 16 silicon PAs together on chip. But there's a lot of limitations due to the passive structures that are required for on-chip power combining. So the fourth that we're going to concentrate on today is arrays of power amplifiers that essentially radiate into free space, and the power is combined in free space. And this has gathered a lot of attention, both from the standpoint of power combining, but also for phased array systems that allow you to steer beams left and right and up and down. So these phased arrays look something like this. These are some chips that my colleague Gabriel Rabiz designed. These are 8-channel phased arrays that basically transmit to 8 different antennas and allow a beam to be steered both when it's being transmitted, that chip on the left is a transmitter, and when it's being received, this chip on the right. But these are huge chips. They're basically the size of Pentiums. And one of the first problems that I looked at UCSD was trying to get rid of this overhead with doubling the cost and the complexity and having 2 different chips that you need to package together. And we wanted to try to combine this together to build a common LNA receive element and PA transmitter into a single front end that was connected to the antenna. So we needed this new circuit. We needed a bidirectional amplifier that could basically sit at the front end and either operate as a transmitter or a receiver. This bidirectional amplifier also serves a very useful purpose after power combining, because the LNA is still required to isolate the noise figure of a mixer, as well as provide enough power to be distributed to each of the 8 antennas in this case. So if we were working at RF frequencies at 2 gigahertz, this is a very well-known problem. Your cell phone does this all the time. And what it does is it has a TR switch between the LNAs and between the PAs, and it has a diplexer. But we don't really have that liberty. We want to transmit and receive at the same frequency. And when we looked at the literature on these TR switches, what we found was that at very high frequencies, above 40 gigahertz, they tend to have losses of about 2 to 3, maybe 4 dB. And if you think about that, that's a lot of loss. That means if your power amplifier can output 1 watt, only 500 milliwatts gets to the antenna. So 500 milliwatts is absorbed in your switch. It's just dissipated as heat. And so that's a very, very, very big loss to take when you are dealing with a millimeter wave PA that doesn't even have a lot of output power to begin with. So we wanted to do something a little more exotic, where we would get rid of that TR switch by basically combining an LNA and a PA into one structure. I like to give credit to people who looked at this before us, and it turns out that in the 3.5 community, about 10 years ago, they ran into this problem, and they suggested a few different techniques to solve it. One was a bidirectional amplifier based on 2 common gate transistors that could basically act as a seesaw. So if you bias one common gate higher than the other, it amplifies from port 1 to port 2. And if you change that biasing, the seesaw will then rotate the other direction and then amplify from port 2 to port 1. But this was the right idea. And so we wanted to investigate something that we called a bidirectional amplifier that was a 2-port network where basically we could change the amplifier from amplifying from port 1 to port 2 to amplifying from port 2 to port 1. Another idea that was floated about 7 years ago now is shown over here, where you basically have 2 amplifiers pointed in different directions. That seems pretty obvious. It's tricky to actually get that to work, though, because of stability issues, because of properly designing the matching for this type of configuration. And we thought that this was the right path because it allowed you to optimize the transmit and the receive amplifier separately, whereas in this common gate seesaw amplifier, basically you don't have the ability to optimize for a transmit and receive. So what we came up with for this PALNA in silicon germanium was to take advantage of what the HBT does very naturally when it's entering different current modes, which is it changes its base resistance and its base emitter capacitance. And we can actually see that the input impedance looking into an LNA, so we have an LNA here on the left and a power amplifier here on the right, that are separated by this transmission line. And the transistor in the LNA is going to basically act as a switch, but also as an amplifier. So we'd like to see the input impedance at port 1 as a 50 ohm impedance at all frequencies that we're interested in operating at, but we'd also like the impedance at ZB, the receive mode, to be an open, so that no power goes into the power amplifier network. In the transmit mode, we want the impedance ZD to seem like 50 ohms so that in transmit mode, all the power goes to the output. But that means in the transmit mode that none of the energy should be absorbed into the input of the LNA. So it's the device's physics that allow us to take advantage of that, since we have not only a Miller effect, the CBC will become amplified, but also the diffusion capacitance of the device changes dramatically as you change the biasing across it. And so, in fact, if you look at this Z1's impedance, it is essentially rotating to a lower impedance in the RX mode than at the TX mode, and that higher impedance at TX prevents any of the energy from being absorbed into the LNA network. So we went out and used this PALNA structure in a bidirectional transceiver that includes not only the PALNA, but a passive mixer, which is inherently bidirectional, and then an IF amplifier operating at 2 to 5 gigahertz, which allows us to get a little gain at those frequencies. We also incorporated a frequency doubler, which allows us to bring a 20 gigahertz signal on chip, and then double that up to 40 gigahertz to downconvert the signal from 44 gigahertz to the IF. So this PALNA is shown in the circuit schematic over here on the right, and is essentially what I just described to you, a transmission line separating the PA from the LNA. This is a full circuit schematic, and I don't expect you to know all these details just to see how we are oriented the transistors. At the IF amplifier, you'll notice we don't use as complicated a transmission line matching structure, and that's because at 2 to 4 gigahertz, we don't really worry about frequency, the power matching at the much lower frequency. But this is what the silicon germanium chip looked like over here on the lower right. To show you that it worked, I'm going to first describe the matching in the 2 modes. So the very important thing that you'd like to see to prove that the PALNA concept works is that under the TX modes and the RX modes, the matching is under 10 dB. And you can see from the blue squares at 40 to 45 gigahertz, in both cases, the RF is actually matched. So that's a good sign. The second thing that we looked at was the RX-TX conversion gain. So this is how much gain you get from the RF port to the IF port, or from the IF port to the RF port in the 2 modes of operation. And in both cases here, you can see that we not only hit our frequency target, so between 42 and 45 gigahertz, but we had better than 30 dB of gain in both situations. So that looks good. In the transmit mode now, we'd like to talk about how much power we were able to get out of the amplifier. And that final PA basically burned about 65 milliwatts to get 10 dBm, 9.5 dBm of saturated output power out at 45 gigahertz. So we were able to actually show that this was relatively efficient. The PAE of the PA at this frequency is 13.7 gigahertz, 13.7%. And for the entire chain, including the doublers, the mixers, and the LO amp, we were operating at 7.5% PAE. In receive mode, we basically measured the lowest power consumption for a receiver at these frequencies, 54 milliwatts, and our minimum noise figure was 4.7 dB at 44 gigahertz. But the real conclusion here is, did the PA isolation network increase noise relative to a RF TR switch? And the conclusion we came to was it was actually much better. When we compared the HBT's minimum noise figure and the simulated noise figure of the PALNA, we find that that minimum noise figure is 4 dB for the circuit and 2.8 dB for the device, which means that we've only really incurred a hit of 1.2 dB to implement this PALNA as opposed to a TR switch. And so if those TR switches are in the order of 3 dB, this is a huge savings in terms of power. But there was one drawback. And if we go back and we look at the circuit, it's pretty obvious where it was. This PA basically is transmitting all its power across the input of the LNA. So if you try to transmit too much power, the transistor acts as a rectifier, right? Which will means that the swing will essentially turn on the transistor. So there is a limit to how well this approach works when you try to transmit very high power levels. In our case, 10 dBm doesn't turn on this device, but at higher power levels, you can get a feedback through that turns on the LNA and then feeds back through the PA. So we wanted to look at other bidirectional amplifier circuit techniques that might be better at these frequencies. And kind of at a concurrent point in time, we had developed a new type of amplifier that's based on traveling waves. We call a constructive wave amplifier. And this amplifier is a little bit like a distributed amplifier, except it only uses 2 ports. And along these 2 ports, there's a transmission line that I have connected between the 2 ports. But what we did that was a little bit different than what people had done before is we broke up this transmission line into tiny little sections of length L. And we wrapped an amplifier around that section of length L in the backward direction, so it provides feedback. And what this allowed us to do was to essentially have a wave that's traveling along this transmission line, and we can detect the ebb in this wave, feed it back through this voltage amplifier, and kick some energy into the peak. So at each of these little tiny sections, we're going to detect the trough in the wave and kick some energy into the peak. And so as you go along this transmission line, you get this amplification of the wave as it's going down to towards port 2. Symmetrically, if you think about a wave going from port 2 to port 1, that means that that wave must be attenuated, it must be absorbed. And there's a lot of very interesting features about this type of amplifier that we tried to describe in a paper a couple of years ago now in TMTT. So you can get a large amount of gain by essentially cascading as many numbers of stages as you need. To give you a little more detail on how this works, basically let's look at this one little cell with a transmission line L and a feedback amplifier AV. We can use a very, very simple circuit model to predict why this traveling wave amplifier works. We have a phase through this transmission line, theta, and we're going to have a delay through the amplifier, the feedback amplifier of TD. That feedback amplifier can basically be modeled as a transconductance, GM, that's driving current into the transmission line with impedance Z0. So we have a feedback gain AV, which is equal to GM Z0 over 2. That means we can derive S parameters that are written in terms of AV, the phase of the transmission line, and the delay through the feedback amplifier. And what you find is that if we want S21, which is the gain in the forward direction, to be large, and we want the backward gain S12 to be small, we get a design condition on theta and TD, which says that we need the delay through the phase through the transmission line to be 90 degrees and the phase through the feedback to be 90 degrees. So what does that do for us? Well, when we plug these conditions in, this lambda over 4, this 90-degree matching condition, we get an S21 that simplifies to 1 over 1 minus AV. And if you've taken a control class, what is that? It's positive feedback, right? It's using positive feedback, not negative feedback, which is traditionally what's implemented in RF or even low-frequency amplifiers. We can use this positive feedback to get amplification. And what's even more interesting is that the feedback gain is less than 1. It's under unity, which means that we don't need a transistor to have a tremendous amount of gain. The transistor can have less than unity gain. In fact, in this case, we've plotted a gain based on a feedback factor of 1/4. And so when the gain feedback is 1/4, we basically get a gain of each stage of about 2.5 dB. So you can think of the S parameters as being, for the transmission line, as degenerating when AV is 0. We simply have a transmission line between port 1 and port 2, which means that any wave will just travel down that transmission line and reach the second port unencumbered. It's same amplitude, just delayed. But as we start turning up the gain, the feedback gain, basically the S parameters start to bow apart. The S12 must be forced down, and the S21 must be forced up. And so this is a very interesting idea in the sense that a lot of the S parameters are controlled through one parameter, which is this feedback gain. The other thing that we noted is that when you look at the matching at the input and the output port, this matching doesn't depend on the frequency that the amplifier is tuned to. It does depend on AV as well. So if you start to turn up AV, S11 and S22 start to rise higher and higher. In fact, you need to limit your feedback gain based only on the return loss that you can accept. So I'm going to come back and describe why this broadband matching is important later on. But for now, we were curious, how well does this work? And we were able to go in the lab, we were able to fabricate a silicon germanium chip that had, I believe this was 12 stages, 15 stages rather, of these feedback amplifiers that were realized with emitter followers and common emitter devices that basically provided that small amount of gain in the feedback path. And we were able to generate 37.5 dB of gain at 100 gigahertz, which is a tremendous amount of gain that nobody's done before. What's more is if you look at this gain and this bandwidth, we were able to get a gain bandwidth product that's over 1 terahertz. So we were able to generate a tremendous amount of gain while not violating unconditional stability. So the technique works. Now what does this have to do with bidirectional amplifiers? Well, it turns out that we can apply this concept by basically putting two amplifiers in the opposite direction along our transmission line. And we can turn on one amplifier when we want to receive, and we can turn on the other set of amplifiers when we want to transmit. All that time, we're not doing anything to the transmission line. So we haven't introduced a switch. We haven't introduced anything that should substantially hurt our noise figure or our gain. And the way we realized this was basically to go back to this SIGI process and to have two amplifiers that are connected through another emitter follower, but they basically go through two different transmission lines. The signal would be tapped from the center of this transmission line and fed into a forward amplifier and a backward amplifier. We choose which amplifier is active by biasing the triode device, the NMOS at the emitter of the device. And so we can turn on all the forward amplifiers by turning VF to a large value and turning VB down, or vice versa. So this is what this amplifier looked like. Basically, we use these serpentine transmission lines because it allows us to keep the path between the base of Q2 and the base of Q3 as close to the emitter of Q1 as possible. We want no delay through that signal path. But we want the transmission lines to be roughly 90 degrees at this frequency. How well did it work? Well, you see this very, very nice S-parameter plot here, where when we were transmitting in the receive mode, S21 peaks at about 16 dB of gain at 90 gigahertz. You'll notice the red curve is our backward propagation, and that's about minus 24 dB of gain at 90 gigahertz. But then when we reverse the amplifier's biasing conditions, this green path now becomes isolating. That is, it attenuates any wave coming in the receive path, while the transmit wave is now amplified. So the reverse port is amplified. And all the same, our stability is ensured at all frequencies. You can see the S parameters for the return loss, S11 and S22, are under 10 dB over the entire frequency range. So what else can we do with this amplifier? Well, depending on how we bias VF, we can change the center of the frequency response by changing the delay through this feedback path. So by adding more resistance here, we essentially speed up the response. And we were able to tune this frequency response from 77 to 90 gigahertz, basically sliding this frequency response from left to right by controlling the voltage that's on those triode devices. But the very, very interesting thing about this is our return loss under all of those conditions didn't change. So we don't have a matching problem with this amplifier. We can reconfigure it to be tuned to different frequencies at millimeter wave bands, but we don't need to reconfigure the matching networks at the same time. So this was a very interesting direction. And when we look at the noise figure and the linearity, these things we're working on now. So the noise figure is about 11 dB. We'd like to be able to push it down to 9 dB by optimizing the LNA for low noise operation. And our output power is limited to about 0 dBm, so 1 milliwatt, which means we need to come up with some clever ideas for improving the PA. And that's one of the research directions we're going in now. I'd like to talk a little bit now about the 45 nanometer SOI process to give you some comparison to how well that process would compete with the SiGe. And these are just some brief anecdotes, things we've recently published and things we're about to publish. This 45 nanometer process, again, has that very, very high-speed transistor. It switches at about, let's say, the FT is about 370 gigahertz. So this is a good process because it's very amenable to digital integration, but it also has some excellent RF behavior. So we were able to show noise figures under 3 dB now at 44 gigahertz, and that compares with the 4 dB I just showed you for the PALNA. So it's very interesting. But how about for amplifiers? Well, it turns out that SOI allows us to do something that we couldn't do at lower frequencies, and we couldn't do with the HBT transistors, and that's stacking the devices. So if you've ever designed an amplifier, you probably are familiar with a Cascade. Are you familiar with a Cascade? Yeah? You've seen a Cascade? Some of you? Okay. A Cascade basically requires that C2 and C3, the capacitors attached to the gates of these transistors, is very large, so that it's an AC ground. All right? But one thing we can do at high frequencies with the SOI devices, the floating body devices, is we can make C2 and C3 be on the order of a few hundred femtofarads. And what happens is we allow the gate voltage to vary, to swing up and down. And by choosing the value of C2 and C3, we can control how much variation, how much swing occurs at V2. But that variation will be, because of the capacitance CGS, will be in phase with the drain voltage at the device M1 and the drain voltage at the output of M2. So we can combine all of these drain voltages that are swinging across each transistor here in phase to get a very, very large voltage swing at the top of the last device. So we go and we break a 7.5 volt swing into 2.5 volts across each of these devices. Said another way on this plot, each transistor's VDS is never greater than 2 volts. And the VGS on each device is never greater than 0.5 volt swing. So we don't break down any of these very, very low voltage devices, these transistors that can only withstand 1.2 to 1.2 volts. We're not going to break them down because we can divide that power across them. If you were to try to do this with a bulk device, you of course have a body on that bulk device. And when you get the very high power levels, the body can bias and has parasitics that end up reducing the effectiveness of this technique. If we want to think about it another way, this is device level power combining. because we can stack these transistors, and some people have theorized that we can stack maybe 10 of these transistors on top of one another using these techniques at these frequencies to get tens of volts of output power out of the transistors. Now this does one other thing that's worth noting. Because we're stacking the transistors, the maximum voltage that can be applied is the number of transistors times the breakdown of each device. That means that the optimum load impedance for the transistor can be increased by a factor of n here as well. So we don't need to have complicated matching networks at high frequencies. We can essentially design our device size to produce a load impedance that's close to 50 ohms at the output of this top device. And that limits how complicated, how much loss we have to incur in our output matching network, and has allowed us to do some very interesting things with, achieve some very interesting results. And one of these results is shown here. This is a 2-stack, so I only have one transistor that's in the stacked FET configuration. And this is very similar to what I just described to you in terms of operation, except I've added one additional inductor here at the interstage node. And this inductor is essentially added just to compensate the phase of the current going through CGS and C3. So it's resonating at the operating frequency. By adding this inductor, we've been able to get output powers that are close to 18.6 dBm. Sorry. Go away. 18.6 dBm, but more importantly, the PAE is greater than 34%. Now, the previous we published record was 25%. So this is a huge jump in the state-of-the-art for millimeter wave PAs, and it's realized primarily through this FET stacking technique. So we think this is a very interesting avenue for future high-power, high-frequency amplifiers. So are there any questions at this point? I'm going to switch gears a little bit. Yes?
Bulk biasing, or not bulk biasing, but biasing up the transistors for these SOI processes.
Yeah.
Is there any sort of special care or sequencing you're taking when you're powering up these devices so that you don't break down the devices while it's being turned on?
Yeah, so we tend to use biasing networks that are based on these resistors. And while I'm acting like these are ideal voltage supplies, we actually have a resistive network that's tied to the supply that allows, as the supply increases, the biasing on each of the gates is increasing. So we try to make sure that we are never providing like 5 volts across a device when it has 0 volts on the gate. So you do have to be careful of that biasing. We've found that these devices will withstand up to 2.5 volts of DC bias across them between the gate and the drain before they break. Any other questions? If something pops up, we can come back to that at the end. So I'm going to switch gears and talk now about high-speed integrated optical circuits. And there's a couple of very interesting things that are developing in this arena. One is trying to move light onto chip-to-chip microprocessor applications, where instead of communicating between multiple cores on a microprocessor, there will be WDM networks that route light between these different cores. And these intra-chip optical networks have been proposed to operate between 5 to 10 gigabits per second with very low power consumption. We use a metric that relates the power consumption to the bit rate, so that you end up getting a unit that's in terms of energy per bit, femtojoules per bit. And so these intra-chip optical networks need to be very low power to keep the microprocessor's overall power consumption low. In this case, under 100 femtojoules per bit. But there's another very interesting application for chip-to-chip optical networks, where people would like to have very high capacity between, for instance, a memory chip and a multiprocessor, a multi-core processor. These applications will require speeds of 10 to 100 gigabits per second, but a little more relaxed energy budget, maybe about 100 times higher, 10 picojoules per bit. So a few years ago, a company called Luxtera investigated this and was able to show 10 gigabit per second communication for these chip-to-chip applications. But they used what was called a Mach-Zehnder modulator, which allowed high-speed modulation. But it also tends to be high power because it's a 50-ohm transmission line, essentially, from an electrical standpoint. Another very interesting optical device that's been proposed over the last 6 years is a ring modulator, which can be implemented in silicon. And it's a very interesting, it has a lot of prospects for this intra-chip optical network because it's low speed, but it also is very low power. And we wanted to look at whether this would also be a candidate for these chip-to-chip, very high-speed applications. So the way this photonic microring resonator works is you essentially have light that's propagating down a waveguide in the silicon process. And that waveguide is basically formed by confining the light between two oxide layers. There's a buried oxide layer in an SOI process, and then there's the silicon dioxide where all of the metal interconnects of the microprocessor are. So you can confine light in between these two oxide layers, and then confine it by doping either side of the waveguide with P plus and N plus. By applying a voltage across here, you basically change the phase velocity around this ring. And so at one critical frequency, light that's traveling down this waveguide will be coupled into this ring. Okay? So it acts as a kind of resonator from an electrical engineer's standpoint. I'm not doing this justice for optical scientists, so please forgive me. But from an electrical standpoint, it's a high Q resonator. And at just the right wavelength, light will jump into this ring and become stored in the ring. The reason that this is low power is that this is basically forming a bunch of reverse bias diodes around the ring. So we have a very simple circuit model for what this ring looks like to an electrical designer. It's a reverse bias diode. And a reverse bias diode can basically be modeled as a capacitor, right? A voltage-dependent capacitor. So these are low power because the energy is going with CV squared. I want a low voltage swing, I want a low capacitance, and then I have a very low energy that's required to modulate this ring. So when we go back and we think of that femtojoules per bit, this is very exciting because I just need to lower the voltage on this ring as much as possible. The question I wanted to look at was, how about high speed? Can I also get high speed while still keeping the power low for the photonic microring resonator? So this resonance, this coupling behavior, is summarized with a Lorentzian line shape. Basically, as I said, at one frequency, light is coupled into the ring. And so the transmission across that waveguide that we described basically shows this dip where all of that one frequency jumps into the ring and is stored. When we want to modulate this Lorentzian line shape, we're going to apply a voltage across it, which shifts that Lorentzian a little bit to a new frequency. So the reason that we get modulation is that our laser will come in at one frequency, at this 1550.5 nanometers, and it will, when no voltage is applied on the ring, that laser light will all be absorbed into the ring. So that's like transmitting a 0 voltage level, right? Because all of the light's absorbed in the ring. But when we apply this voltage, just 2 volts, now suddenly that Lorentzian shifts, and the light will pass right past the ring. And that's like transmitting a 1. So what we need to do is basically keep our extinction ratio, this ratio of 0, the P out power and the input power, the power associated with 0 and the power associated with 1, to be as high as possible. And what we end up finding is that that requires a larger and larger voltage swing, right? So there's a trade-off. If I want a high extinction ratio, I want to be able to shift this Lorentzian as far as possible. But that means that my voltage swing must be higher, which means my CV squared energy goes up. And it turns out that this trade-off also involves bandwidth, because the delta lambda, the line width here, we could imagine that being broadened. And if that line width was broadened, that basically would also force us to have more voltage swing to get a certain extinction ratio. So if we think about achieving a reasonable extinction ratio, and in the optical community, better than 8 dB is kind of a common goal, it turns out that the voltage we need to apply across this diode increases from about 1.5 volts for a line width of 0.1 nanometers to more than 3 volts for 0.25 nanometers. So that means if we want more bandwidth out of the ring, we need to drive it with more voltage. So it's not obvious that we get better energy efficiency in terms of this femtojoules per bit. So we wanted to try to use a relatively low bandwidth ring that required a lower voltage swing and still get high speed. So our microring resonator from an electrical circuit standpoint looks like two bandwidth limitations. One is the RC limitation, that depletion capacitance of the diode, and a series resistance associated with it, which is like an electrical RC time constant. But there's also a time constant associated with the photon lifetime in the ring. And it turns out that these two time constants are, for the sake of argument, roughly equal, about 12.5 gigahertz. So we shouldn't be able to modulate these rings faster than 20 gigabits per second while still maintaining the extinction ratio of 8 dB. In fact, if I simulate these ring dynamics and I simulate them at about 25 gigabits per second, you can see the eye closure. So instead of transmitting a clean 0 and 1, basically the region in which we actually get accurate communication is decreased to this small eye, this diamond-shaped opening. So we wanted to look at a couple types of channel coding that could compensate for this bandwidth limitation. And the first is called duobinary modulation. And maybe you've taken a class in comm theory, maybe you haven't. But the basic idea of duobinary is to take binary data, zeros and ones, and map it into three levels, 0, 1s, and 2s. In the process of mapping zeros and ones into zeros, ones, and 2s, we can reduce the bandwidth of that binary sequence. So we go from requiring a bandwidth that's something like 1 over the bit rate to something that's about 1/2 of the bit rate. So binary modulation allows you to decrease the required bandwidth. Now this was really interesting in the case of the ring modulator because we could use an electrical duobinary modulation, and by modulating around this null, we can get an optical NRZ signal out. So the ring itself does the decoding for the duobinary. We simply are using that modulation to overcome the bandwidth limitation of the ring, and we don't need any changes to our receiver because the ring itself will decode the electrical duobinary into NRZ signals again. So we just need to figure out how to align our zeros, ones, and 2s such that we get the right data sequence out of the optical NRZ, out of the optical modulator. The way we do that is by adding a very simple duobinary precoder. This is kind of a simple result. It just requires an XOR that's fed back to itself through this D flip-flop. So this requires a little more digital power consumption. But once we've done that precoding, we're able to get a very nice three-level signal by level shifting our signal around a VDD rail and a VSS rail. So the actual duobinary driver is two inverters. One that's centered at a VDD of about 1.5 volts, and one that's centered around a negative supply of minus 1.5 volts. The reason I'm able to use these negative supplies again is that I'm using SOI. So the body is isolated from the transistor, and I can play with the rails a little bit. But the point of the story is that the different information sequences that are sent to these two different inverters will cause the three-level signal that I need to produce the duobinary modulation. So this is what the chip looked like. It's actually very large. It's about 4 millimeters on one side and 0.8 on the other. So I've cut off this area here because it's basically just dead silicon that's required to bring in an optical probe. So when we're testing this, the optical probe is brought in and brings laser light in here on the left through this grating coupler. There's a long waveguide through the silicon substrate that then comes up to our duobinary transmitter. The ring is shown here. And basically, you've seen this picture before. I showed this at the beginning. But the ring is just this purple area. The light then, it goes past the ring and comes back around off chip to another grating coupler where we can monitor the transmit eye. So I wanted to kind of show this quick movie to show the testing, how we can go about testing these rings. They're very fascinating. For an electrical person, you don't get to see a lot when you're testing. You just kind of trust that the RF signals are going into the chip. But with optics, you can actually see the light through an infrared camera. So this is an infrared camera image of this light waveguide traveling across my silicon chip. And what we're doing is we're tuning the wavelength of the laser across the Lorentzian line shape of the modulator. And so as we're getting closer and closer to this null, you can see that light is getting absorbed into the modulator, which means that that's where the deepest part of the null is. So as the more light is being absorbed into the resonator, basically that spot gets brighter and brighter to show the higher intensity. You can also see that the light is evident through the waveguide as well. That's occurring because there's just a gradual amount of leakage through these on-chip waveguides that shows up on the infrared camera. Once we pass the center of this null, you can see that this spot is getting less and less dark, which indicates that we've moved away from the null. So we use this to basically get a profile of the Lorentzian line shape. Which shows the tuning behavior that's required to modulate a 0 and a 1. So I'm not going to get that back, I guess. This is the output I at 15 gigabits per second. We're monitoring the optical power level. So this is about 400 microwatts peak-to-peak swing for the NRZ optical signal that we get out of this modulator. So this is basically pushing the data rate for on-chip optical networks to higher speeds than people have seen before, particularly using ring modulators. We're able to consume only 45 milliwatts from the analog section of the circuit. So this is a power consumption that's under 3 picojoules per bit. So it's extremely low power, and we've been able to push the data rate to higher speeds than before. But you might say, why not just use other channel coding techniques like preemphasis? These are well known from from the serial link community. A lot of the high-speed memory links that in your computer today will use some form of preemphasis. And you can, in fact, use preemphasis as well to try to compensate for these bandwidth limitations. Basically, the preemphasized waveform tries to swing over the nominal 0 and 1 voltage and then back to the actual value. So you end up using more of the null on one side to produce a preemphasized waveform, but in the end you'll get this optical NRZ signal out. So in simulation we can predict that the NRZ, that the preemphasis will open the eye substantially using just a little bit of extra headroom. So the gray lines are what I showed before for the data eye, the black line is what I'm expecting to see. This circuit implementation is a little bit different. As opposed to using a lot of digital processing to produce the duobinary signal, we can do preemphasis directly at the driver by modifying our inverters to basically be something like an AND. When we want to preemphasize the waveform to go from ground, for instance, to a rail higher than VDD, we basically produce a path that is gated by the current data and the previous data. And when those two values are different, we pull the modulator up to a higher voltage rail than we would nominally if the two values were the same. We pull it up to VDD. And so if we provide this delta VH and this minus delta VL on all four of these arms, we can basically produce a preemphasized waveform across the cathode and the anode of this reverse bias modulator. So we got very similar results. Without the preemphasis, we were only able to modulate the ring at about 20 gigabits per second. And you can see the eye closure is asymmetric, which is what we predicted from our simulations. But when we added the preemphasis, we were not only able to get an open eye at 20 gigabits per second, but we were able to push this data rate as high as 25 gigabits per second. So we found that preemphasis was a little more successful at pushing the speed of the on-chip optical rings but yet it does consume slightly more analog power consumption because of the overhead associated with this more complicated driver structure. Okay. Where am I with time? Couple minutes? Okay. I'm going to skip these things, and I'd like to talk about one more circuit demonstration. We looked at, previously I told you a little bit about this constructive wave amplifier. And I'd like to talk about one more way we can use it to push the bandwidth of circuits. Some work we did that set records. And this goes back to using a silicon germanium process, since we demonstrated the constructive wave amplifier with the silicon germanium process. We wanted to try to use this relatively low FT process to push a bandwidth of a circuit over 100 gigahertz. And you would predict, based on these two numbers, that the transimpedance would be very low. Basically, we'd be limited to something under around 50 ohms of transimpedance. But that's based only on a shunt feedback amplifier with a resistor RF from the input, connected between the input and the output. But it turns out if we use this constructive wave amplifier, basically you know from what we've described that it's a feedback amplifier that points in the direction of the output of this shunt feedback amplifier and uses a transmission line for feedback. This can end up providing a much broader bandwidth than we got from this original transimpedance amplifier. And we call this multi-stage equalization because basically the first transimpedance amplifier can have a frequency response that rolls off at a much lower bandwidth, a 3 dB bandwidth of 46 gigahertz. While the constructive wave amplifier can compensate by having a gain that peaks at a much higher frequency, around 100 gigahertz. Now, the reason that these two can be equalized is that the constructive wave amplifier's frequency response is rather gradual. So the slope of the roll-off can be compensated with the slope of the roll-up. The other thing that works for us is the return loss, S11 and S22, are under 10 dB at all frequencies. So you can actually cascade these things. We can put them together, and we have return loss that's matched over all frequencies up to 120 gigahertz. So this kind of equalization turned out to work very well. The simulated result is in this white circle, and the actual measured frequency response is in yellow. And we got a very, very beautiful flat frequency response all the way up to 102 gigahertz with under 1.5 dB of ripple, which was a record itself. We were also able to get a group delay that was under plus or minus 4 picoseconds over that entire 100 gigahertz of bandwidth, all while consuming only 73 milliwatts. This is about a power consumption about 10 times less than previous 80 gigahertz amplifiers. So this technique worked very well. On top of that, our transimpedance is 10 times greater than we anticipated. So when we went in and we measured this in the lab, we found that we're not only able to get a 40 gigabit per second eye very cleanly on an optical test bed. This is our optical test bed with fiber controllers and power monitors and photodetectors. But when we took the S parameters and we put it into HFSS and ADS, we're able to show operation as high as 160 gigabits per second in simulation. We don't personally have data generators that work at those frequencies quite yet, but we're very hopeful that these kinds of circuit techniques can push the state of the art for silicon for several years into the future. So in summary, I've given you a huge overview of what's going on in our group, partly in the area of silicon-based millimeter wave systems. I've showed you a PALNA technique, a way of trying to eliminate the complexity of both transmit and receive phased arrays by integrating the PA and the LNA into a single element. I've tried to show you a little bit about bidirectional amplifiers and how we can use traveling wave circuit techniques to build bidirectional amplifiers. And finally, some of our latest results for SOI CMOS, which show that SOI can solve many of the device-level problems that are facing bulk CMOS at these frequencies by using stacking techniques. Additionally, we've shown a little bit about what we're working on with silicon photonics. Mainly, this is modulating rings at very high frequencies and trying to overcompensate the bandwidth of the ring using duobinary channel coding and preemphasis for channel coding of the modulator itself. Additionally, I hope you've seen how we can use some of the circuit techniques that I described to push the bandwidth of circuits to new limits. And with that, I'd like to acknowledge the funding I've received over the last 5 years, which has largely come from DARPA, as well as some NSF grants and industry support through Panasonic and the Center for Wireless Communications. So I'd like to thank you for attending and welcome you to UCSD. If you're ever down in the area, please stop by and say hi.
All right, thanks a lot, Jim. Hey, we have a time for 2 or so questions. I'd like to open it to Richard.
Do I use IBM?
Yes, IBM for all the processes. We do some things with TSMC, but I haven't presented that here. Yeah. No.
Another question?
No? Okay.
So what about for some of the on-chip photonic work, were there any special process options besides the need for SOI? Besides that, was it purely
It was a pure
standard?
It's a pure off-the-shelf SOI process otherwise. And so I work with, I don't design the photonic devices myself. I work with a group at Oracle who has gone through the rigor of building the photonic rings. And actually, this chip, this is kind of ugly work. This SOI chip that I showed you earlier was huge. It's 4 millimeters by 0.8. And we actually sent out 5 different versions of it that had small tweaks to the ring modulator. So this is an immense amount of area just to get one working chip. Those small tweaks in the ring are changing the coupling coefficients and basically changing the sharpness of the Lorentzian line shape that I was describing.
Okay.
So using their kind of models and their expertise, we're able to just take a ring that we know will work and build the circuits around it.
Okay.
Yeah.
Cool. Any other questions?
A shy group.
Actually, I did have one more. I think we have
Yes.
time. Oh, Chris.
So in the amplifier where you were using the positive feedback,
Yeah.
I guess the natural question would be, how do you guarantee stability over the process voltage and temperature? I would think the stability is pretty well guaranteed because you're going to have difficulty getting gain at those frequencies, but how would you control then the gain? I think is probably the more practical question. Stability is probably not an issue. But
It's an excellent question. So I may have glossed over this. While we have positive feedback in each amplifier, we can introduce negative feedback in the feedback amplifier itself. And the way I introduce that feedback amplifier, that negative feedback, is through an emitter degeneration resistor. So we actually taped this chip out back in 2008, and it came back and it worked the first time. And the reason is that it is actually really stable against PVT because of the amount of negative feedback that I can introduce in each amplifier cell. So the transistor itself, because it doesn't need, it actually has a gain of maybe 2 dB at this frequency. But I can actually use that negative feedback to reduce its gain down to about 1/4. So all that negative feedback in the end will help me compensate against PVT.
the net feedback is positive, correct?
The net feedback is positive across the transmission line. I'm just talking about the active part of the circuit, the emitter follower and the common emitter. That has negative feedback. So the actives, you can introduce negative feedback for the actives themselves. But the net effect through the transmission line is then positive feedback, exactly. Yeah, but you're right. There's some more work to do into really showing a lot of sample sets and showing that the PVTs are actually really good overall corners. Yeah.
Anyone else? So for your modulator, you did pre-emphasis where you momentarily jack the voltage above VDD or below.
Exactly.
Why not just run it above VDD the whole time? Is the trade-off?
CV squared.
Okay, just power.
You know, and it's a small savings because if you're dealing with duobinary, if you're dealing with equiprobable ones and zeros, then a lot of the time you are going to jack the voltage up and down. But in the end, you consume a lot more power going to the higher supply rail. The other thing is if you always keep the supply high, you end up incurring, you don't get the preemphasis bandwidth compensation, right? It's really the waveform that jumps up to the higher value that is providing you with the bandwidth compensation.
Cool. Well, thanks everyone for coming. So let's thank Jim again.